we have some fake data, which were discussed in previous video in this playlist. Here is a data set in which x and y are linearly related. Here is a data set in which there is a second order polynomial relationship or a parabola. Those are both curves that can be fit using linear regression, and that's what we're going to talk about in this video. Subsequent video, we'll talk about the nonlinear regression required for the power law data. So let's take a look at the notes that we generated on my iPad in an earlier video. So recall that this is a linear data set, and we're trying to minimize the sum square e sub I term or the sum square residual term, and this leads to two equations in two unknowns, a0 slope and a0, which is the intercept, a1 is the slope. Those are your unknowns, and this boils down to this equation, a matrix equation, or we could talk about in terms of this equation. These are actually the same or equivalent treatments.
Very quiet. Shh.
If anyone would like a free dog, please let me know. So I'm going to start with this first formulation of linear regression. Okay, so this is the same MATLAB script that we worked in the previous videos. So let's start. Okay, so we need to formulate this matrix. Let's see if I can get it on the screen at the same time. Remember, our data are in these variables. The x values are in x series. The y values are in y data 1. So now let's define our matrix. Let's say M. So n is the number of data points. We get that out of length of x series. And the sum of the x values is just the sum of the x series. And then we need the same thing again. We'll make MATLAB do the calculation twice, and we'll do the sum of each of the x series terms raised to the second power. That we just formulated this matrix. And sorry, I forgot to type the m equals. Okay, so now we have this vector, which I call b. I usually think of this as m times x equals b. So let's formulate the b matrix as, or it's a column, still a matrix. Sum of the y data, and then the sum of the products of the x data and the y data. So the way I do that is x series times the transpose of the y data. Okay, so I'll keep the semicolons off. Let's run this. I typed something wrong. Line 68. I've done something wrong. No, first of all, these should be square brackets. Okay, I don't want to see this x series. I also don't know how to type. Okay, where was x series output earlier? Here. Okay, so there is my matrix M, there is my vector B, and assuming I typed it right, I can say the A linear fit is going to be M slash B. So the solution to the matrix problem, M slash B. So let's see what that is. I'm also outputting the quadratic function, which I don't really want to see. Okay. So this should equal, the best fit slope and intercept should equal A0 and A1. They're scattered in the data, so it's unlikely they're going to be perfect. Okay, so the linear fit, it looks pretty far off actually, but maybe 46 is close to 50, but 25 doesn't seem all that close to 3. Let's go back and plot the best fit next to our actual data. So I'm going to go back to figure 3, and I'm going to say subplot 3, 1, 1. Let's do a hold on. And I'm going to now plot X series, or actually let's say Y best fit linear, and that's going to be A linear fit. The first parameter is the slope. The second is the intercept. So these are going to be the predicted best fit. Let's see how we do with that. Okay, so in figure 3, the red line corresponds to the calculated best fit for the for the data set. We are concerned about the slope, but I think on this scale, it's still pretty close to 0. I think so. Given the scatter in the data, I don't think the slope is off. To me, that does look like a good fit. So remember that we talked about an alternative formulation for the linear regression. So let's try that calculation. I said it was equivalent. So if I was right, we should get the same slope and intercept. This is the one with the Z matrices. Okay, so if I say A1, this is going to be a vector. I have to define my Z matrix, but I'm just going to put the formula so you recognize it. Z transpose times Z times Z transpose times Y data 2. Oops, Y data 1. Okay, now I have to define Z here. So the first column of the Z matrices is just 1s, and then the second column is the X's. And by the way, this alternative formulation should match this formula right here. So I think the easiest way to do this is to say X series to the power 0. So any number to the power 0 is going to be 1. And then x series to the power 1 is going to be 1s, and I'm going to do transpose to turn the rows into the columns. And if I did this correctly, we're about to find out, then, oh, whoops, I didn't actually display the answer. Do remember that the actual best fit numbers are going to change because we're using random number generators. So this time, the linear fit using the matrix equation, the slope was 51. It should have been 50. The intercept is 7.5. It should have been 3. And notice that this A1, which was derived using our Z transpose Z equation, is identical to the slope and intercept that we got from the other formula. So in other words, I made the claim that this equation was equivalent to this equation. I didn't actually prove it, but I still haven't proven it. But hopefully you'll agree that at least this time the answer is the same. So the same calculation can be used on the second data set, which was quadratic. So hopefully you'll see why that's a convenient So we need to expand this. This is for data set 2. So let's call this A2. And the Z matrix now needs to have a quadratic term, which is that third Z function. So we have 0th order, 1st order, and 2nd order. And now we are applying the formula to 2nd order quadratics. And we should get the best fit parameters for that quadratic. So we got something. Now let's see if we can plot it against the second data set and whether or not it see whether or not it agrees with the data. So y best fit quadratic equals A2 1 1. That's the constant term. A2 2 1 is the term that is proportional to x. And then A2 3 1 times x series squared. And now we can have a plot x series and y best fit quadratic, which should agree with data set 2. Okay, I have done something wrong. Fendi, stop it! Fendi, down! Sorry, that was my dog trying to dig a hole in the couch. Okay, so what did I do wrong here? Inverse Z transpose Z. That should have been the second data set. I don't see anything wrong. A22. don't see what's wrong with that. 3, 1, 2. Oh, I think it's not that the calculation is wrong. It's that I erased the data. There we go. Okay, so now this quadratic goes through the data. I think that looks pretty good. It's clearly curved. And we may want to compare it to the original parameters B0, B1, and B2 that we used to generate the data. So let's take a look at that. B0, B1, B2. Okay, so it's supposed to be 1, 4, and 7. This number is pretty close to 7. Perhaps that's pretty close to 4. Minus 10 doesn't strike me as being very close to 1. But if you look on the scale here, the intercept, if you look at the scatter and the data, there's a lot of uncertainty in the intercept. So I think that we have succeeded in doing a linear regression of a straight line data set and a second order polynomial data set.